Section 9.3, Rational Functions and Their Graphs. Rational function f of x is a function that can be written as f of x equals p of x over q of x, where p of x and q of x are polynomial functions. The domain of f of x is all real numbers except for those for which q of x equals 0. And we know when our denominator becomes 0, our function becomes undefined. Before we look at a rational function, we need to understand a few things. First, we have to take a look at vertical asymptotes. We've done this in our previous sections. But let's look at a few more rules that apply to a rational function. First of all, the rational function f of x equals p of x over q of x has a point of discontinuity for each real 0 of q of x. In other words, when the denominator is 0, we know the function's undefined. So we know something has to occur there. Either there'll be a gap in our function or a hole, or there'll be a vertical asymptote. Number 2, if p of x and q of x have no common real zeros, then the graph of f of x has a vertical asymptote at each real 0 of q of x. And the third, if p of x and q of x have a common real 0, such as a, then there is a hole in the graph or a vertical asymptote at x equals a. And we will take a look at situations that apply to these three rules. Next, we can have horizontal asymptotes. And here's the rules that apply to that. The graph of a rational function has at most one horizontal asymptote. Number 1, the graph of a rational function has a horizontal asymptote at y equal to 0 if the degree of the denominator is greater than the degree of the numerator. 2, if the degree of the numerator and the denominator are equal, then the graph has a horizontal asymptote at y equals a over b. A is the coefficient of the term of the highest degree in the numerator, and b is the coefficient of the term of the highest degree in the denominator. And step 3, if the degree of the numerator is greater than the degree of the denominator, then the graph has no horizontal asymptote. Something else occurs when this happens, but we'll have to take a look at that in a different section. I'm sure those 3 previous slides sounded quite confusing, but when I take a look at a rational function, we can apply those rules quite easily. So let's take a look at this example. I have f of x equals x over x squared plus 2. By my definition, my numerator is x, that is p of x, and it's a polynomial. My denominator, q of x, is a polynomial, that is x squared plus 2. The first thing I want to do is to determine what values of x make my denominator 0. To do that, I set my denominator, x squared plus 2, equal to 0, then solve for x. Those values are the values that make my denominator 0, which would identify discontinuity, which would be holes or asymptotes. So let's solve for x. X squared equals a negative 2. Take the square root. X equals plus or minus the square root of a negative 2. And then I simplify further. I have x equal to plus or minus. That gives me the square root of 2 times the square root of a negative 1, which is plus or minus I square roots of 2. That tells me I have no real numbers that make my denominator 0. Therefore, this function has to be continuous. So I have this statement. There is no value that makes the denominator 0. That means the graph is continuous. That means there's no breaks, jumps, or holes, which means I'll have no vertical asymptotes because I don't have a value in the denominator that becomes 0. But if I take a look at the rule for horizontal asymptotes, I have a horizontal asymptote at y equal to 0 because the degree of the denominator is greater than the degree of the numerator. The degree of the denominator is 2, while the degree of the numerator is 1. And when that occurs, I have a horizontal asymptote, even though I don't have it shown here, at y equals to 0. And you're going to notice something very interesting about my graph. You can see my graph intersects the horizontal asymptote at 0, 0. Vertical asymptotes cannot be crossed, but horizontal asymptotes actually can be crossed. But horizontal asymptotes really look at the ends of the function. And therefore, if you notice at the ends of the function, they get extremely close to my horizontal asymptote, but do not cross it. And that's what's interesting and what's important about horizontal asymptotes. On my next example, I have the function f of x equals x plus 1 over x minus 2. My p of x for the numerator is x plus 1. My q of x is x minus 2. The first thing I want to do is find out if there is any location for discontinuity. To do that, I look at the denominator, which is x minus 2, and I set that to 0, and I solve to find any values of x that would make my denominator 0. So here, when I solve, I get x equal to 2. And as you can see, x cannot be 2 because it makes the denominator 0. 2 minus 2 is 0, which makes my function undefined. Therefore, there is a vertical asymptote at the value. Here, at 2, I have a vertical asymptote. That is the location of my function that is discontinuous, and that's why I have a vertical asymptote. Now, let's see if I have any horizontal asymptote. From a previous slide, we know the rules apply if I have a degree in the numerator equal to a degree in the denominator. And that would give me a value of y equal to a over b. In other words, the coefficient of the largest degree in the numerator is 1. The coefficient of the largest degree term in the denominator is 1. Therefore, y equals 1. And as I've stated here, horizontal asymptotes at y equal 1 because the degree of the numerator and degree of the denominator are equal. Then we use y equals a over b. And when I simplify, that's y equals 1 over 1, which is 1. So I have an asymptote at y equal to 1. And now we have our graph of the function, and we have both branches defined in our coordinate plane. In our next example, a rational function equals the quantity of x minus 2 times the quantity of x minus 3 all over x minus 3. In this type of situation, I can simplify and cancel my x minus 3 and x minus 3 and end up with y equals x minus 2 and use that to graph this rational function. But I still have to keep in mind the situation I have in the denominator, which is x minus 3. So I still might have a place of discontinuity. To do that, as I have in the previous slides, I set that denominator, x minus 3, equal to 0. And then I solve. X equals 3. So this function has discontinuity at x equal to 3, even though I'm going to graph x minus 2. So I don't have an asymptote because x minus 2 is a straight line. I have a discontinuity, which will be a hole in my graph. Next, I need to take a look at horizontal asymptotes. If I would FOIL the numerator, I would end up with a degree of x squared on the numerator and an x on the denominator. In other words, the degree of the numerator is greater than a degree of the denominator. In this situation, as I've written, since the degree of the numerator is greater than a degree of the denominator, there is not a horizontal asymptote, and we don't have one in this problem. Therefore, what I do is I graph y equals x minus 2. My y-intercept, -2, and I have a slope of 1, up 1 over 1, and I continue through. But at x equal to 3, I have a hole in my graph. And that means I don't have a value associated with that because it makes my function undefined. Therefore, this is my graph of my rational function. On the previous slides, we've seen points of discontinuity in graphs as vertical asymptotes and as holes in a graph. Here's the definition. A point of discontinuity occurs if a is a real number for which the denominator of a rational function f is 0. Then a is not in the domain of f. The graph of f is not continuous at x equal to a, and the function has a point of discontinuity at x equal a, either at a location as a vertical asymptote or as a whole. And we've seen that in the past 3 slides. Now, let's take a look at some samples. Find any points of discontinuity for each rational expression. Here, I want to solve the denominator for any value of x that would make this 0. To do that, as in the previous slides, I set that to 0. X squared minus 3x equals 0. Here, I notice that I need to factor, so I'm going to factor out an x. That leaves me x minus 3 equals 0. Set each to 0, x equals 0, and x minus 3 equals 0. Therefore, I have points of discontinuity at x equals 0 and x equals 3. At these locations, I would have vertical asymptotes. To go a step further, even though it didn't ask me, I can find my horizontal asymptotes. So these are my vertical asymptotes. Now I can find my horizontal ones, if there are any, and I notice that the degree of my numerator is 2, the degree of my denominator is 2. Therefore, when the degrees of my numerator and denominator are equal, I know I have a horizontal asymptote at y equal a over b. A is the coefficient of my degree of my numerator, the largest one, which is 1, and b is the coefficient of the largest degree term in denominator, which is 1. Therefore, I have a horizontal asymptote at y equal to 1. Let's continue to the second example. Again, I want to find the points of discontinuity. Therefore, I need to find values of x that make my denominator 0. So here I have x squared plus 9 equal to 0. That's the procedure. And then we solve this. X squared equals a negative 9. Take the square root of both sides to get x equals plus or minus the square root of a negative 9, which we know is plus or minus the square root of 9 times a negative 1, which we know that's going to be x equal plus or minus 3i. Therefore, I have an imaginary value, and therefore I have no points of discontinuity, or none. Again, I know they didn't ask this, but let's see if there's any horizontal asymptotes. Again, the degree of my numerator is 2. The degree of my denominator is also 2. Therefore, they are equal. The coefficient of the largest degree in the numerator is 1. The coefficient of the largest degree in the denominator is 1. And therefore, I have a horizontal asymptote at y equal to 1. Just to take this a step further in each example. In this example, find any points of discontinuity for each rational expression. Here I have y equals x squared minus x minus 12 over x squared minus 16. Step 1, I want to factor the numerator and denominator. And when I do, I'm going to get x minus 4, x plus 3 in the numerator, and my denominator, difference of squares, x plus 4, x minus 4. I can cancel my x minus 4 out to simplify, and I can graph this rational expression to represent my original, which is x plus 3 over x plus 4. But I have to keep in mind my original denominator. So I need to find values of discontinuity. In other words, I need to set x plus 4 equal to 0. When I do and solve that, I get x equal to a negative 4. Since that doesn't get canceled out, that is my vertical asymptote. But I still have to consider my x minus 4 that gets canceled out. So I set that equal to 0, and x equals 4. But since that gets canceled out, that only makes this a hole in my graph. It's still a point of discontinuity, but it's not an asymptote. It's a hole in my graph. I can verify this by taking a look at my graph. So I graphed x squared minus x minus 12 over x squared minus 16, and I get this diagram, or this graph. As you can see, I have a vertical asymptote at 1, 2, 3, 4, negative 4. As a matter of fact, since the degree of the numerator and degree of the denominator are equal, the coefficients of those largest degree terms are 1 and 1. Y equals 1 over 1, which is 1, gives me a horizontal asymptote at y equal to 1. Now, those are my points of discontinuity for my vertical, but I said there was a point of discontinuity at x equal to 4. And I can verify that in my graph by going to second trace, which would be calculate. I want to calculate a value. And I want to calculate x equal to 4. And you will see the calculator has no response because we know at 1, 2, 3, 4, there should be a hole in my graph. So if I graphed it, there would be a hole here. The calculator doesn't designate it, but we know that is the true value, which means it's undefined at x equal to 4. On this example, again, I want to find the points of discontinuity. Here's my rational function, which is y equals 5 over x squared plus 2x minus 5. Normally what I'd like to do is factor my polynomial expression. But in this case, I can't factor that expression. But I still need to find the values of x that would make my denominator 0, if there are any. To do that, I'm going to use the quadratic formula. And I've plugged in my values, and I've solved for the values of x that make my denominator 0. That would be x equals approximately 1.45 and approximately a negative 3.45. And these are going to be my vertical asymptotes. And that is the location of my points of discontinuity. And I can check that out on a calculator. When I graph my function, I get a graph that looks something like this. And I can point out the asymptotes here, approximately 1.45 and approximately a negative 3.45. 1, 2, 3, about here. And that is the location of my discontinuity in my graph. On this example, I want to describe the vertical asymptotes and the holes. First, on the rational function, I want to factor. So I'm going to factor a negative 1 out of the numerator to make sure my x squared comes first. So a negative 1. And that would give me x squared minus 4. If I distribute back in, I would get the original. And on the denominator, I have x squared minus 4. I know that'll cancel, but I still need to factor again to find my values of x that might provide some discontinuity. So that gives me a negative x plus 2, x minus 2 in the numerator, because it's difference of squares, and similarly on the bottom, which is going to give me x plus 2, x minus 2. And that will leave me, when I simplify, y equals a negative 1. In other words, I'm going to get a horizontal line, but I'm going to have some discontinuity at these two values. Therefore, when I set this to 0, I'm going to get x equals a negative 2. When I set this to 0, I'm going to get x equals 2. Therefore, I'm going to have holes at these two locations. So if I graphed it, I would get a graph that looks like this, but at these two locations, I should have a hole at x equals a negative 2 and x equals a positive 2. On this function, I have y equals 5x squared over 5x squared minus 5. Again, I want to factor. That gives me 5x squared. Factor a 5 out of the denominator. It gives me 5 times the quantity of x squared minus 1. I have difference of squares, and I can cancel the 5s, which leaves me an x squared. Factor the difference of squares, x plus 1, x minus 1. And I have vertical asymptotes at x equal to a negative 1 and x equal to 1. These are vertical asymptotes since nothing got canceled from either of these expressions. Again, I want to find the asymptotes and holes. I want to factor y equals x minus 5, x plus 1, factor a 2 out of the denominator, x squared minus 2x minus 3 gives me y equal to x minus 5, x plus 1 over 2 times x minus 3, x plus 1. The x plus 1 can cancel, which gives me y equal to x minus 5 over 2 times x minus 3. I have a vertical asymptote at x equal to 3, but I have to consider when I cancel my x plus 1 over x plus 1, I still must consider that. Therefore, at x equal to a negative 1, I have a hole. So here are my positions of discontinuity. Finally, y equals 3x squared over factor x squared plus 1. Y equals x squared over x squared plus 1. Here, I have no points of discontinuity, so none, because I don't have any values of x that would make my denominator 0. For example, x squared plus 1 equals 0. X squared equals a negative 1. When I take the square root of both sides, I get x equals plus or minus I, which is imaginary. Here I want to find my horizontal asymptotes. It's easy to do that right off the start because I know the polynomial degrees here, 2 and 2. When that occurs, I need the coefficient of the largest term in my numerator, which is 1, coefficient of my largest term degree in the denominator, which is 3. Therefore, I have a horizontal asymptote of y equals 1/3. Here, the degree of the numerator is greater than the degree of the denominator. And when that occurs, I have none. There are no horizontal asymptotes. Again, I have a function, but in this function, when finding a horizontal asymptote, I realize the degree of the numerator is less than the denominator. When that occurs, I have a horizontal asymptote at y equal to 0. Again, my degree of the numerator and degree of the denominator are equal. When that occurs, the coefficient of the largest degree term in the numerator over the coefficient of the largest degree term in the denominator gives me my horizontal asymptote at y equal 5 or 2.